Yeah. So up to this much, so we did in the last class. So this was the solution for an underdamped system. So here, if you just compare this solution, so with the basic equation of simple harmonic motion, so what you will get, that this is the amplitude, this is the magnitude of the amplitude for a damped vibration, and this is the natural frequency, because earlier in undamped free vibration of single degree freedom system we found the equation as x equals to a sine omega t, okay, or omega n t. So here this is the damped natural frequency, so this coefficient of t, okay, so this is the damped natural frequency and its value is under root 1 minus zeta square into omega n, okay. So if you just plot, okay, or if you just want to see the graphical representation, okay, or the pictorial view of this equation, then you can plot it against displacement against time, okay, and finally you will get a reduced amplitude in every cycle, okay, and finally the system will be in stable condition and the vibration whatever it was acting on the system, so it will vanish, okay. So here for this locus, okay, or locus, so you will get one time period, okay, on this time axis. So let's say from here, okay, so from here to here, if you just take the time duration, so this will be the time period, but this is not exactly equal to that in the undamped free vibration. This is the damped time period, okay, because damping is there, so it is td. So in the next cycle, so it will again 2td, okay, then 3td, like that. So you can take the multiplication in terms of integer multiplication, okay. So this is displacement time curve or plot of an underdamped system with general initial condition, okay. So initial displacement is x naught, that is why x naught, from x naught the graph is started or the plot is started, okay. And if you just see the profile, okay, the outer profile of this graph, so what you will get, so you will get an envelope, okay, you will get an envelope. So this envelope, it is having an amplitude of a2 e to the power zeta omega n t, okay. So as t changes, okay, because e to the power minus t, okay, something multiplied, that is zeta omega n, it is constant into t, so exponentially decreasing, okay, amplitude you will get when you will plot. So here in this underdamping condition, so one very important term, that is logarithmic decrement, actually came into picture, because this is exponentially decreasing. The amplitude in each of the cycle is exponentially decreasing, okay. So here it is written free vibration of an underdamped system, okay. Consider 2 points. We will consider 2 points, point A and point B, okay. So corresponding to ta and tb means at time ta, t small t, it is not capital T, so at time small t suffix a and at time small t suffix b. So let's say we have got 2 points, we are having 2 points, point A and point B, okay. So at these 2 points, so what you are able to find out, so you are able to find out the amplitude, because you have got the expression of this one, Okay, x naught under root 1 minus zeta square e to the power minus zeta omega n t. Okay, so what will be then tb minus ta? So the time period, okay, means these 2 points are chosen in such a way that the time period actually executes by this system. Okay, means from here to here, whatever it is distance from a to point b, the distance is same. Okay, so tb minus ta, so will give you the time period of this vibration, under damped vibration. So what will be the time period of vibration, under damped vibration? That is 2 pi under root 1 minus zeta square omega n, means 2 pi by the circular frequency. Okay, earlier it was in under damped condition, it was 2 pi by omega. Here it is 2 pi by the damped circular frequency. Okay, under 1 minus zeta square omega n. Okay, so what is actually logarithmic decrement? So it is defined as the natural logarithm of the ratio of any two successive amplitudes on the same side of the mean line. So what is the mean line? So this is the mean line. Okay, and it is said that natural logarithm, it is the ratio of the natural logarithm of any two successive amplitudes. Suppose this is one amplitude. Okay, so here this is one amplitude and this is the next successive amplitude. So natural ratio of the natural logarithm of these two amplitudes on the same side of the mean line, means if you are considering one amplitude here, then again you need to consider the amplitude here only. Okay, successive amplitude, not this amplitude, because on the same side of the mean line. So that is called as the natural, or that is called as the logarithmic decrement. Okay, under damping condition. So here one question actually it arises. So the natural logarithmic decrement occurs in which type of vibration? That is under damping vibration, because all the other damped vibrations, that is over damping and critically damping, they are not vibratory signal. Okay, because they are aperiodic in nature. Okay, so now the height of the displacement time curve at t equals to t equal to the height of the envelope at the same time, means at xa. Okay, so at ta, what will be xa? Means what will be the amplitude? So how you will be able to find out the amplitude? By this expression. Okay, by this expression or this expression. So how it will be written? That is x naught under 1 minus zeta square e to the power minus zeta omega n ta. Okay, so x naught 1 minus under 1 minus zeta square e to the power minus zeta omega n ta. So xb will be similarly, you can write x naught under root 1 minus zeta square e to the power minus zeta omega n tb. So we need to find out the ratio, isn't it? So how you will be able to find out the ratio? So just you have to divide, because we need to take the natural logarithm, isn't it? Then only you will be able to find out the logarithmic decrement. By this definition, it is the natural logarithm of the ratio of any two successive amplitudes. So xa and xb are the two amplitudes which are on the same side of the mean line. Okay, so xa by xb will be equals to e to the power minus zeta omega n, so ta minus tb, isn't it? So if it is in the denominator, this term it is in the denominator, so this will be cancelled out and it will be only simply ta minus tb. Okay, so minus term it is there, that is why you can reverse it. So tb minus ta you can write. Okay, this tb minus ta is what? This is the time period, isn't it? Time period of this undamped vibration, damped vibration under damping condition. So what I will be writing, that tb minus ta, because e is here. Okay, so you can write what? 2 pi, because this was what? The time period, isn't it, of undamped this damped vibration, under damping vibration. tb minus ta will be 2 pi by omega n. So 2 pi by under root 1 minus zeta square omega n, 2 pi by omega d. basically. Okay, so then you can replace this tb minus ta by this term. Okay, so zeta will be remain same. Instead of this omega and tb minus ta, or instead of this tb minus ta, we will be writing this one 2 pi by under root 1 minus zeta square. Okay, omega and omega n will be cancelled out, so you will get this one. So if you just take the natural logarithm, so log of xa by xb, this e term will vanish, so 2 pi epsilon under root 1 minus zeta square. Okay, so this is called the logarithmic decrement and is denoted by delta. So this is the delta. Okay, that is the logarithmic decrement. So this is basically denoted by this delta. Okay, so just I am sharing my screen. I am muting myself. Okay, I have an important call to receive. Okay, just you see that I will just sharing in my screen. Okay, so yes, actually you didn't ask me one thing. Okay, so here I have written that this amplitude value. Okay, so what was the expression? A2 e to the power minus zeta omega n t. Okay, but here I am writing that xa equals to x naught under divided by under root 1 minus zeta square. Okay, so e to the power minus zeta omega n ta. So from where this actually coefficient comes? Earlier I was writing a1 and a2. Okay, so actually one homework I gave you in the last class, that you need to solve, because in the last class only we found out what this expression in x. Okay, so we didn't solve for c1 and c2, isn't it? So again you need to differentiate it with respect to t, then you will get what? X dot velocity. Then after that you need to put the initial condition, and finally you will get an expression, so where you will get an equivalent, okay, expression of this kind. So if you just find out the value of a2, so what you will get? So it will be x naught divided by under root 1 minus zeta square. Okay, and here all this term will change. Okay, so this is an homework, this is a homework to you. So you need to solve it. Okay, and you need to show it to me also when I will ask you to do an assignment. Okay, because in one assignment I need to give you, so in that assignment those things will be given to you. Okay, so finally you will get one expression where this a2 will be x naught divided by under root 1 minus zeta square. That is why at any instant I can write the amplitude. Okay, at any instant means at any instant of time. So here ta is the time and here tb is the time. So here xa is the amplitude and here xb is the amplitude. So what is logarithmic decrement? So delta is the logarithmic decrement, which is log natural log of the ratio, okay, means xa by xb. So we are going to find out this xa by xb. So at xa, the amplitude is this one, because a2 value is what, x naught by under root 1 minus zeta square, so e to the power minus zeta omega and ta. Okay, so instead of this ta or tb minus ta, so we will be putting the damped time period. Okay, so here tb minus ta, we are putting this one, so you will get the natural logarithm ratio as 2 pi zeta divided by under root 1 minus zeta square, and this is the value of the natural logarithmic decrement, okay, or the logarithmic decrement, because by definition, so it is the ratio of the natural logarithmic decrement, okay, the consecutive amplitude, successive amplitudes on same side of the mean line. So here this amplitude should be on the same side of this mean line, on this equilibrium line on the upper side, okay, means on the same side you are taking the successive amplitude, so that will be the logarithmic decrement. So this logarithmic decrement, you cannot take the other half, okay, or or you cannot skip any means any successive amplitude. You cannot take this ratio, this divided by this. You need to take the ratio x naught by x1, log of x naught by x1, or log of x1 by x2, or log of x2 by x3. Then only you will be able to define it, and its value is constant. Okay, log of x naught by x1 equals to log of x1 by x2, log of x2 by x3. So that value is constant. Okay, so for small values of zeta, so this the logarithmic decrement value is 2 pi zeta. Okay, so this term actually vanish, it is exactly equals to 1. Okay, if this is very much small, zeta is very much small. Okay, and for n cycle, suppose for one cycle, this is for one cycle, isn't it? For one cycle you are taking the two consecutive ratios, and for n cycle this delta is given by 1 upon n log base e x naught by xn. Okay, so we can prove this one. So how it will be like this actually, by taking the basic concept, so we will be able to find out that this logarithmic decrement for n cycle will be this much. Okay, so here you can see that x naught represents the amplitude at particular maxima, and xn represents the amplitude after a further n cycles, means after a number of cycles. Okay, so how you can prove that one? So you know that x naught by x1 equals to x1 by x2 equals to x2 by x3. So it is what means xa by xb. Okay, so same thing, x naught by x1, x1 by x2 equals to x2 by x3. So it will be equals to e to the power 2 pi zeta under root 1 minus zeta square. So here it is written. Same thing, e to the power zeta omega and td. Okay, same thing, it is e to the power zeta omega and td. Okay, so this ratio, so here it is written like this, so it is constant. Okay, so here it is equals to constant. Okay, or e to the power delta. Okay, though it is not distinct, so here I am just telling to you that equals to constant and equals to e to the power delta. So what will be delta then? So you need to take the logarithm. Okay, so log base e x naught by x1 equals to log base e x1 by x2 log base e x2 by x3 up to log base xn minus 1 by xn, because this is one unit reduced. Okay, so here how many this term will be there? There will be n delta term will be there, n terms will be there. Okay, so this ratio is, the value is what? Delta, isn't it? Because we have got this ratio value, it is delta. So if you just multiply the n terms, so what you will get? So you need to multiply this delta by n. Okay, so n delta will be equals to, you need to multiply all those terminologies. Okay, so log base e x naught by x1 multiplied by x1 by x2 up to xn minus 1 by xn. So you can see this x1 will be cancelled out, x2 will be cancelled out, x3 will be cancelled out. So xn minus 1 and xn minus 1 will be cancelled out. So finally what you will get? So log base e x naught upon xn. Okay, so then you can find out the delta from this expression. That delta will be 1 upon n log base e x naught upon xn. So which was the expression I wrote. Okay, here. So for n cycle, the value of this natural logarithmic decrement or logarithmic decrement is this one. So you need to remember this one, because directly questions are asked based on this formula. Okay, and you should know this basic. Okay, so basic formula. So from here, so zeta, if zeta value is less than 1, so this denominator value can be make equals to 1, and this delta will be equals to 2 pi zeta. Okay, so this is the logarithmic decrement method. Yeah, it is written. Logarithmic decrement method is often used to find out the amount of damping in a physical system. Okay, so yeah, from this expression, because you will be able to find out zeta value, isn't it? If all these ratios are given, xa is given, xb is given. Okay, so you will be able to find out zeta if other terminologies are given, isn't it? So you will be able to find out zeta value, damping factor value. Okay, and this is the case for this is the representation for linear damping, isn't it? Or linear vibration. Okay, linear under damping vibration. For angular this deflection also, so you will get values in angle. Okay, so here you may get values in some means linear values. Okay, means 2 units, 3 units, like that. But your values may be in degree also. This x not and x1, it is not necessary that they will be only millimeter and the centimeter, all these kind of things, but they may be in angular form also. Okay, so successive angular deflection may be given. So angular deflections are also the amplitudes in angular vibration, isn't it? So yeah, or transverse vibration. So there we need to put the value of the successive angles, okay, of the same side of the mean line. Then you will get the logarithmic decrement. Okay, so for today's class, it is I am just stopping myself here. So one important thing actually I need to share apart from this class. Okay, so just be with me for 5 minutes. Okay, so up to this much, just you note it down in your copy. Okay, I'll be sharing this video in the Google Classroom also. I think, yeah, so just you note it down. Okay, so wait.